Hello, my name is Consuelo Castro, and I will be going over the solution for problem A13 in homework set 5. In problem A13, the rate constants for the first order decomposition of an organic compound in solution are measured at several temperatures. From this information, you are asked to calculate the activation energy. Before we solve for the activation energy, let's recall two terms that we are familiar with. First is the rate constant, K, which defines the relationship between the rate of a reaction and the concentration of reactants, and is independent on concentration and only dependent on temperature. The units are in seconds for a first-order reaction. Our second term is activation energy. EA is the energy required to start a reaction. The units are kilojoules per mole. Activation energy is demonstrated in this graph. It's the minimum amount of energy needed for the reactant to undergo a reaction. In order to solve for the activation energy, we will be using the Arrhenius equation. The Arrhenius equation demonstrates how the rate constants vary with temperature and activation energy. The equation states that K, our rate constant, equals to A, the number of collisions, multiplied by E raised to the negative EA, our activation energy, over R, our gas constant, and T, our temperature. In order to solve for the activation energy, we will ln both sides and get ln K equals ln of AE raised to the EA over RT. Through further rearrangement, we ultimately get ln K equals negative EA over RT plus ln A. To put this equation into slope-intercept form, I will take out the 1 over T, demonstrated here, and get ln K equals EA over R multiplied by 1 over T plus ln A. As you can see, this corresponds to Y equals mx plus b, where the slope will equal to negative EA over R, or EA equals negative R times slope. Given this equation, we will be able to plot our values and obtain a slope that we will use to ultimately find what our activation energy is. First, we must convert this temperature from Celsius to Kelvin by adding 273 degrees to each of these temperatures. Once those are converted, we can plot our Y and X values. Our Y value is going to be ln K, so we're going to ln each rate constant. Our X axis will be 1 over T, so once our temperature is in Kelvin, it will be 1 over that Kelvin temperature. Once we have obtained all our new values, we will be able to graph our values, x-axis being the 1 over T, and the y-axis being ln K, and find our slope. Once you have carefully plotted your values, depending on what software you use, I use Excel, I was able to get my slope. And as you recall, the activation energy equals to negative R times slope, and R is simply our gas constant, which is 8.3145 joules Kelvin per mole. Now, as you recall, activation energy is in kilojoules per mole, so we will have to convert these joules into kilojoules by simply times 10 over negative 3. Once we have converted this rate constant into kilojoules, we can simply multiply it by our slope that we obtained was 12,044 negative. Don't forget your negatives. Ultimately, you will get an activation energy of 100 kilojoules per mole for this reaction.